I've opened up tree.java in the chapter 17 class notes folder. Um, we are going to write some basic code and we're going to spend all of like, I don't know, 10 minutes on this, which is on it, what we call an arbitrary tree, a general tree, a tree in which each node can have an arbitrary number of children. After today, we're not going to do anything with trees like that. Okay, we're going to focus on trees that can have um, 0, 1, or 2 children only, and that will be our focus here shortly. But I want to start with this more general case. This is still a useful data structure, as we talked about a couple of days ago. This is the data structure we would use to represent like file directory structures, right, with folders and files and stuff, as an example. So certainly still useful. What's interesting about our tree class here, so there's a lot of different ways to do trees. And so we're not using like a standard Java library one. I don't know if there is a standard Java library one. I'll try to get an answer for that for tomorrow. Um, but often we end up writing like our own tree class. You're going to see some similarities between the tree class we write and the linked list class that we write as well. Um, so a tree class only has one instance variable, and our one and only instance variable is of type node, and it's the root. So the only instance variable in the tree class is the root of the tree. From the root of the tree, we can do everything else. Um, so the root of the tree refers to a node. Conceptually, this is like a linked list node, but it's a little bit different. Um, the way it's the same, or the way not the same, but the way it's similar is a node still needs to hold on to some sort of data. Again, just for simplicity, the tree class that we're writing together is not a generic. So the type of the data is just going to be of type object, as opposed to like making this a generic of type T. I suppose I could have done that. You all know how to do generics now, but we're going to leave it as object for now. Um, and then here's where it's different than a node in a linked list class. A node in a linked list class has a reference to the next node. In a tree, like there is no next node. And then in this arbitrary tree instead, what we need is we actually need a list of nodes, which are all of the children. A given node can have multiple children. And so we need to store all those children in a data structure. So we're going to use a list. I'm using the type list, which is like the interface type. When we actually make the list for the children, we'll use like an array list or something. All right. I had some starter code here from you that we're going to use in a moment, which is to compute the size of the subtree whose root is this node. Um, you're gonna see like much like we did with linked lists, actually different than we did with the linked lists. We defer more of the computation to the nodes as opposed to the tree. Whereas in the linked list, we did most of the computation in the linked list and not really the nodes. And that's just a different approach here. But given that these nodes are a little bit more sophisticated, it seems to work out well. So we'll come back to the size method later. Um, I want to complete the rest of the methods here. So as usual, I've written the Java doc for you and the method headers. We're going to fill in the body. So here's our constructor. And when we construct a brand new tree, we get a tree with one node, the root, and no children. And so this constructor here has one parameter, which is the data for the root of type object. And we need to actually make a new tree with that data. So this will seem familiar to like what we did last chapter. We need to make a new node. So we're going to say this dot root equals new node. Very, very similar to what we did with the linked list. And then we'll say this dot root dot data equals the root data. And this dot root dot children, there's no children, but we don't want to leave this instance variable null. So we still want to say new array list. So that we won't get like null pointer exceptions. We simply have a list with no elements and therefore no children. Right? That's all it takes to make our node. It can be tricky to like build up a tree. And so the approach that we're going to take is we build a tree and we always start with just a tree with one node, just with the root. But then we can always take an existing tree and add another tree as a child of that. Okay. So we can like add a subtree. So this method here, add subtree, takes one parameter, which is the subtree, and we're going to add it as the last child of the root, right? Because the root could have multiple children. This new subtree is going to become the last child of it. Once we code this, we'll look at an example and you'll kind of see how this all goes together. But building up a tree is a little bit awkward in my opinion. So it takes kind of some planning on how it goes. All right, so I'm going to say this dot root dot children dot add. So I'm calling lots of methods, subtree. We have the squiggly red underline. This doesn't compile, right? I now have a compiler error. With your neighbor, take a moment and discuss how do we fix this compiler error? That's step one. And step two, what conceptual mistake did I make? What was I confused about in terms of our tree data structure? Shift Control P will open up the command palette and then type settings. And you want that one, settings UI. Yep. All right, step one. How do we fix my compiler error? What do I need to change here? Subtree what? Someone said subtree dot root. Excellent. So that's how we get it to compile. What error did I make? Yeah, root is private. Yes. I don't think that was related to the compiler error. Or well, it wasn't related to my confusion. I purposefully made the mistake today. In the last year, this was like I just made the mistake. I'm like, oh, this is kind of a good thing to talk about. The error said you're trying to add like a tree or a nodes tree system. Yeah, I've got like the wrong type of object, right? And I think that's something that makes all of this tree code tricky is that we have to keep the tree separate from the nodes. Just like in the linked list class, we had to keep like the linked list separate from the nodes, but I think it's easier to do that with the linked list class. I know I and many students struggle to keep the tree and the node separate when we're dealing with the tree class, even though you're mostly comfortable now with keeping like the node separate from the data, right? The object. So like we've fixed one of those type issues, but not the other one. So this is a really common mistake. I made it last year. I see lots of students make it. So yeah, so I got to say subtree.root so my types match. All right, let's talk about that's all we need. Isn't that crazy? We can now build like an arbitrary tree with just those methods. How cool is that? But it's more useful if our tree does something useful. So let's actually implement this public method to calculate the size of the tree. The size of the tree is defined as the number of nodes in the tree. That's another one of our academic vocabulary terms. So let's implement size. An approach we're going to take a lot in this chapter is in our tree class, we're going to defer responsibility for doing these calculations to the node itself. So for the size method here, we're simply going to say return this dot root dot size. We're going to basically tell the root of our tree, that node, hey, you figure out the size and just return it because I don't want to do that. So now I think it makes sense to go up here to the size method. And this method computes the size of the subtree whose root is this node, and it returns the number of nodes in the subtree. This is inherently a recursive operation. Trees love recursion. So let's do our typical recursive part. What is the simplest subtree to calculate the size of? We just have one node. So let's create a local variable called sum equals 1. And then sometimes we'll just return the sum, right? Like if there are no children, we'll just return the sum. But if there are children, so that's our terminating case. There are no children, we'll just return the sum, and we'll make sure we jump from here to here in a moment. But if there are children, then we take one small step towards the solution. The small step is this node counts 1. And we ask each child node to calculate the size of its subtree, right? That's our classic recursive approach. So we're going to use an enhanced for loop for each child in children. Again, like verbally, I talk Python because I think it makes more sense, but I'll type it as Java. So for each child in the list of children, sum plus equals child dot size. So if we have no children, that for loop isn't going to execute, and we're simply going to return a value of 1. But if we do have children, for each child, we're going to add the size of that subtree to sum, which we've initialized with 1 to count for the root. Okay. Again, I think this is a great example of where recursion makes a lot of sense conceptually and works out really well. So once you have this typed, we can switch over to tree demo. Here's like some demo code I wrote that just constructs the subtree starting with and that we've been focused on in like our warm-up activities today. So you'll know it's a little weird, right? Like I make a tree for Anne, I make a tree for Peter. I add Peter as the first child of Anne. I make a tree for Zara. I add Zara as the next child of Anne. I make a tree for Savannah. I add Savannah as the first child of Peter. And then I print out the size of the tree rooted at Anne. So when I run this, we should see like it's size 4. That's what we would expect.